This is an introduction to organometallic reagents. Organometallic reagents consist of a carbon and metal bond, and in this case, the electrons are being pulled towards the carbon, and so the carbon acts like a carbanion, and it can be a base or a nucleophile. The three types of organometallic reagents that we will look at are organolithium reagents, where there's a carbon-lithium bond, organomagnesium reagents, also called Grignard reagents, where there's a carbon that's bonded to a magnesium and bromine, and organocuprate reagents, also known as Gilman reagents, where it's a carbon bonded to a copper. Gilman reagents are less reactive than organolithium and Grignard reagents. To prepare organolithium and Grignard reagents, we start with the alkyl halide, and we treat it with the metal that we want to introduce. So for organolithium reagents, we start with the alkyl halide. We treat it with 2 equivalents of lithium, usually in a nonpolar solvent like pentane or hexane, and then we generate the organolithium reagent and 1 equivalent of the lithium halide. Grignard reagents also start from the alkyl halide. In this case, we treat it with magnesium metal, usually in an ether solvent like diethyl ether or THF, and we form the Grignard reagent, where we're making this carbon-magnesium bond. Organocuprate reagents are prepared from organolithium reagents. In this case, you're going to treat it with copper iodide, and that prepares the Gilman reagent. Organolithium and Grignard reagents are highly reactive and need to be treated with care. They are both strong bases and strong nucleophiles. In order to prevent your reagent from reacting with the solvent as a base, the solvents must be aprotic, that is without an acidic proton, and anhydrous, that means without water. Some of the common solvents for organolithium reagents are hexanes and pentanes, and this is usually because you prepare them in these solvents, and then you can also do the reaction in THF. The common solvents for Grignard reagents are the solvents that they're usually prepared in, which is diethyl ether or THF. The reason diethyl ether or THF or other ether solvents are used is because they can stabilize the organometallic reagent by forming a complex. The next thing to consider is the halide used when preparing organolithium or Grignard reagents. The halides of choice are bromine and iodine. They work well, efficiently, as well as quickly. Chlorine is slower to react, and fluorine is mostly unreactive and is rarely used. These reagents can function as both a base as well as a nucleophile. Let's first look at its function as a base. Now, they're very strong bases and will react with acidic protons. So, for instance, if you started with bromobenzene and you treated it with magnesium in diethyl ether, the first thing you're going to do is create the Grignard reagent. And so you create this carbon-magnesium bond, and now this is a strong base and can react with water. And so it can attack the proton in water and produce benzene. This is not a very useful reaction. This is why you want to eliminate water from the reaction. Benzene is cheaper than bromobenzene, and there's no need to do this entire reaction in order to make more benzene. Usually, these reagents, if they're used as a base, will be used to deprotonate functional groups and sometimes to prepare other strong bases. For instance, LDA. N-butyllithium is used to prepare LDA by treating it with diisopropylamine in THF. These reactions are usually done under low temperatures, and the product is going to be deprotonation of this acidic proton. Remember, the pKa here is about 35, so while it's not very acidic, this is a strong enough base to be able to deprotonate it. And so your product is going to be LDA, which is a strong non-nucleophilic base, and butane. Remember that the pKa of alkanes is about 50 to 55, and so you can see that even though this proton here is not that acidic, it is going to favor the product because this is the weaker acid. Organometallic reagents can also act as nucleophiles, and they are very reactive nucleophiles. Remember again that organolithium and organomagnesium reagents are stronger and more reactive than Gilman reagents. And if you were to treat benzaldehyde with cyclopentyl magnesium bromide in diethyl ether at 0 degrees, you're going to have nucleophilic attack of the Grignard reagent onto the electrophilic carbon of the aldehyde. This results in the formation of your tetrahedral intermediate. So overall, this is a nucleophilic addition mechanism, and you will make this tetrahedral intermediate. You have that hydrogen still on, and now you've made a bond with the cyclopentyl group. Upon workup, so step 2 would be workup with either mild acid conditions or with water. Upon workup, you will protonate that alkoxide to make the alcohol. So your final product is going to be an alcohol. Now pause the video and predict the major products of each reaction, keeping in mind that there will be a workup, where necessary, to neutralize any charges. In the first reaction, you've got an epoxide and you've got ethyl lithium. Now ethyl lithium is a nucleophile and a base. You're treating it in dioxane, which is just another example of an ether solvent, at low temperatures. You know that with epoxides, if you treat it under strong nucleophilic conditions, you're going to undergo an SN2 mechanism, and that is going to result in attack at the less hindered side of the epoxide. And this is going to open the epoxide, and upon workup, you're going to protonate that alkoxide, and you end up with this final product, which is the methyl group going to the back. You've got the alcohol coming out, and since it was an SN2 attack, your ethyl group is also going at the back. In the second example, you've got an organolithium reagent, and you've got a compound with a bromine as well as an alcohol in it. You note this is an acidic proton, and so the result is going to be an acid-base reaction where you have deprotonation of this alcohol. And so your compound is going to be the protonated alkyne and your deprotonated alcohol, which upon workup is going to protonate, and you end up with the starting material again. In the final example, you're treating this ketone with allyl magnesium bromide in THF. You're going to have nucleophilic addition. So this nucleophile is going to add into the carbonyl carbon, and after protonation, you're going to end up with an alcohol. So you have an alcohol, you've got a methyl group on there, you've also now introduced your allyl group, and you still have the remaining part of this compound.